My title is not AI in astronomy, but a little bit more fancier, advancing new frontiers in astronomy data analysis and discovery with artificial intelligence.
Oh, sorry. If I had known that was the title, I would have.
Yeah, Adam made up the title and just put it on the schedule. So, all right.
I was close.
Close. Yeah. All right. So let's just orient ourselves. So I work in the area essentially of scientific machine learning, which falls sort of in the middle between traditional scientific computation and machine learning. So on the traditional scientific computation side, we would consider that few data in the sense that you could spend millions of hours running a single simulation. In scientific machine learning, we have some data, but maybe not as much data as people who are training models that are scraping the layer. Now, in terms of theory, right, the advantage of traditional scientific computing is that you have a very well-defined theoretical model. In scientific machine learning, maybe you have some missingness in the problem. So you have a semi-complete idea of what's happening, and then there's no predictive theory in the machine learning AI side. So before I dive into applications of generative AI in this field, first I want to talk about why astronomy data is challenging. So basically give you an idea of the scope of the problem and some terminology that I'm going to be using. So as the introduction said, I work on studying how stars like our sun form. Now, this is a hard problem because the initial conditions of star formation for our own sun were erased billions of years ago. So we basically look out into the universe and try and find other examples. So another example, starting on the galaxy scale, these galaxies are forming stars in regions all over. And so we try to use that as analogs. So if we start on this scale, 150,000 light years, we can zoom in to a region like this one. This is the Taurus liquid cloud that's forming a cluster of stars, thousands of stars. So zooming in by several orders of magnitude. We can zoom in still further and we get a dense core. This is a region that would form an individual star system like our own. So down at the kind of 1 light year scale. Zooming in still further, we get an accretion disk with channels material onto the star, and this is on the order of 15 light hours. So altogether, this is spanning something like 8 orders of magnitude in spatial scale. If we talk about gas densities, then it's 24 orders of magnitude in gas density. So there's a huge dynamic range to this problem and a really broad range of physical data. But there are a lot of processes that start on the smallest scales and impact the largest scale. So we can't just decouple an individual system from its whole galactic environment. So for example, forming stars will launch energetic bipolar jets, which launch material at hundreds of kilometers per hour. Then you have more massive stars, which have solar winds. So these are much, much more powerful than the solar wind that we have. We have a really weak wind, even though it impacts the satellites. Sometimes these massive stars have such high velocity and energetic winds, they sweep up and produce these really huge bubbles. And last but not least, the very massive stars go supernovae and they kind of return all of that production of heavy elements back into their environment. So altogether, this circumscribes a cycle of life. So there's a huge amount of physics here and a lot of very interconnected scales. And in half of my research where I'm not using IA, I'm doing traditional approach to scientific computing, that is forming stars inside computers. So what I mean by that is we have a set of partial differential equations that describe the underlying physics, gas motions, namely hydrodynamics, gravity, radiation, magnetic fields, and the stars themselves. So one example might be the Poisson equation, where given some density distribution, you solve for potential at every point in the domain. So we start with some initial conditions, an initial molecular cloud. We feed it into our code to compute the evolution of these equations. And at the end, you get a simulated star cluster. So I will give you an example of what this kind of calculation produces. And it's easiest if I show you a movie of what we get at the end. So the movie you're going to see is a fly-through time animation of what is happening within the simulation. And it's color-coded by density and temperature. Low density is purple, orange is kind of intermediate, and high density is white. And then you'll see the appearance of yellow-green gas. So it's going from kind of very cold, neutral gas to ionized hot gas. You can see that there's a lot of structure in this cloud. This gas is supersonic, so it has Mach numbers of 10 or 20. It's moving at very high velocity. As gravity begins to take over, you'll see these sort of white regions. Those are the high density regions that are pre-stellar and are beginning to collapse to form stars. So as those collapse, eventually you'll see signatures of the stellar feedback in the form of these bipolar high velocity jets. So there's one of the first ones going off on the left. You can see over time it's getting more and more clustered. So stars are not forming in isolation. You can see these complex filaments, and stars are forming sort of clustered together. There are regions that are already forming tens or hundreds of stars within this cloud. Altogether, this is following 20,000 solar masses of gas, 20 million particles, and forms about a few thousand stars at the end. Once the massive stars turn on, you'll begin to see winds. Those are the bubbles in the top portion. So as these stars are forming, you can see them sweeping up and expelling gas. There are black regions there that is seen through the cloud. At the center there is what we would call an optically revealed star cluster. So the gas has been dispersed and you see the stars directly. And this continues to evolve and only stops evolving when the supernova from the most massive star turns on and goes off, which is very soon.
What's the time scale?
About 9 million years. There it goes.
Is that the time scale for computation?
It feels like it. Sometimes it feels like it, but no. Yeah. All right. So why did I show you that simulation? What does that have to do with generative AI? And basically, these computational models serve as excellent labeled training data, because even though we might have only a few of these simulations, we have complete physical information. And so generative AI is basically the glue that allows us to couple these computational models with the observational data. So for the first part, I'm going to talk about one example, which is predicting human relationships from observational data with generative AI. So the fundamental problem that we have in astronomy is that we observe photons. So we observe the light. We don't directly observe the physical variables that we would actually like to measure, like density, temperature, magnetic field. And instead, we need to take the light and infer these quantities from the observations. To make matters worse, we don't have a complete radiative spectrum. We only have maybe a few wavelengths, and there are lots of complications. Our data is noisy and messy. We have limitations and biases, and so it's an extremely messy data problem. So our goal is to build a model that predicts the stellar heating from a cloud like this one. This is the Monarch 2 star-forming region. So our input is going to be maps of the observed infrared light. We're going to predict without information about star locations or properties. That is, we only have the distributed light. We're not going to tell it where the point sources or clusters are. We want it to be smart enough to ignore foreground and background contaminants, because you might have stars in front or behind the cloud, which are not actually providing heating. And then the output is the total radiation field, radiation energy from all sources that are responsible for heating this cloud. So we're going to use a denoising diffusion probabilistic model to do this. I think you heard a talk about this yesterday afternoon. These are excellent for generating images. So the denoising component works well for us because it's basically learning the underlying transformation between one set of data, noisy data, and another. And it's maybe not a surprise that this is very useful in a scientific context because this is inspired by the principle of diffusion, right, from physics itself. So we use our computer models as training set. We make synthetic observations, which is shown in the top left. So this is sort of the analog to what we would observe if we were looking at the simulated cloud as if it were a real object. So this is a simulated 3-color, 3-band infrared image. We run it through the model, and then we predict what's in the bottom left. This is the distributed total radiation energy density in that field. So training is goes pretty well. We train it on about 10,000 of these synthetic cubes. And then we get this really nice correlation. If you're paying attention to the axis bars, you can see this spans more than 5 orders of magnitude in dynamic range, which is one reason why astronomy data can be very tricky. You can see visually it's doing a pretty nice job. The dust emission inputs on the left, and then you can see the target and then the prediction. So at least by eye, it is actually doing an amazing job. So that's an amazing job on simulated data. What happens if we go and we run this on a real cloud like MONAR 2? So this is a Spitzer observation of MONAR 2. Here's the contours of the predicted stellar heating that we can fade out to the map. You can see it actually does a pretty good job. Even though we haven't told it where the stellar clusters are, it has successfully identified them, and it produces a map that spans several orders of magnitude in radiation energy density and does generally a pretty good job. Right. So one of the questions I often get when I'm doing this work is, well, your simulation, as amazing as it is not real data. So how do you know that it's doing a good job? So we spend a huge amount of our time applying the models to out of distribution data to basically constrain just how bad we might be doing, just in case. So this is one of the more extreme test cases where we take a simulation and now we put it in a radiation field that's 100 times higher. And so this is data the model hasn't seen before. It's completely out of distribution by a very large factor. And we can do the same test again. So the 1-to-1 line for predictions in black, and then the 10-to-1 line is in blue. And where those points are, it's off by about a factor of 3. So maybe a factor of 3 is not so good for medical science, but for astronomy, where we're talking about powers of 10, anything within a power of 10 is amazing. And considering that this is out of distribution by a really huge amount, this is actually a really incredible performance. The next thing people ask me is, well, all right, well, why can't you just analytically predict the distribution? Surely you have the physical equations. Can't you just predict what's going on? And the real problem with this is that these marker clouds, as we saw, are just super complex, super messy. They have all these distributed sources. So you have a lot of incomplete information. So there is some classic theory, which predicts a power law relationship between the inferred temperature of the dust that's emitting the light and the total radiation field. But as you can see, this does a terrible job, right? So the data is clearly not following that relationship. And this is because there's all these distributed sources. This only takes into account if you have the gas just quietly sitting there being irradiated, and that is definitely not what's going on. And there's also additional uncertainties in measuring the underlying dust temperature, given, again, that you only have a few bands. So all in all, this is a huge step forward compared to what we can do classically, and it really allows us to glue our knowledge about the astrophysics from the simulations to the observational data directly. All right, so next I'm going to talk about correcting astronomical images with generative AI, right? So you may have noticed in the previous plot that there was this sort of open pixel there, that was nothing there. And this is because the underlying Spitzer data is saturated. There's a really bright, massive star there, and it just has no data, right? It just can't record that information. So in astronomy, we have lots of data, but we also have a lot of bad data and a lot of ways it can go wrong. So one is instrumental errors. So we use these CCDs, and they have these artifacts, which create streaks on the image. We can have legitimate but annoying data, like foregrounds. So you're trying to look at a bunch of stars, but there's this really annoying dust in the way. And there's the Elon Musk foreground, which is Starlink satellites that are frequently going across our field of view, a problem that's getting worse and worse over time. And so you can imagine that there's a lot of corrections that we would like to do in a really automated, intelligent way. So let me mention the traditional way of doing this. Traditionally, what we do is we take two images and we compare them. So I'm going to talk to you about this in the case of transients. So what I mean by transients, that's things that go flash in the night, like supernova is the most common one. So these can create changes that occur over seconds, hours, days. So basically, we take two images like this, and just looking from one to the other, you can probably spot some of the difference. But we basically take the two images taken at two different times and then subtract them, and you can immediately see the transient crab and transient palm tree, right? So here's a real example. This is a galaxy where the supernova has gone off in the spiral arm over here. And this is a really nice example because that is a very bright supernova. It's away from the center, and you can pretty clearly see it by eye. But even so, you can see that there's some problem issues potentially by doing typical subtraction. The image on the right is a little bit blurrier than the image on the left. And so you do have to take some care, even in the traditional way. You have to do this with some intelligence to try to identify things that are important differences versus not important differences. All right. So what happens if you have a much more hard case? This is a galaxy, high redshift galaxy in the very early universe taken by JWST in 4 different wavelength bands. So what if you happen to have had a supernova that went off and it's somewhere in that galaxy? Maybe it's just hard to pick out. Maybe you only have one epoch or one image, and you would like to separate or create a model of the underlying galaxy and then subtract that off to find supernovae. So basically, this is the problem, right? So can we create generative models for these galaxies to sort of infill some missing regions in the data? So this example is using a mass generative image transformer, using in-painting. So here's what happens, right? When you apply this to a dog, if you remove this part of the dog, you can get predictions for what that dog looks like underneath that mass region. And, some of these are better than others. And so it's a whole complicated problem of which is the best image you can pick. All right, but here's what happens if we apply this to the JWST image, we mask out a region, and then we get a set of predictions. Right. So I want to stress that at this point, we haven't modified the training data at all, and the training data does not include any astronomy images. It definitely doesn't include any JWST images, and the image is very recent, within the last year. And so this is pretty good, right? So it's pretty good, but what's missing now in the next steps are to go through and determine if this is scientifically useful. So if we generate a bunch of possibilities, how do we pick the best one? Maybe we do some ensemble averaging. Is this actually efficient for picking out various transients? How much better can we do if we actually train on underlying galaxy images? So there's a huge amount of potential here in applying these kind of generative techniques to astronomy images. All right. So the next topic I want to talk about is generative AI in terms of connecting the observational data to the data users. That is, in terms of searching and exploring data. So I want to tell you not about a finished problem, but a vision that we have. And this is a vision that I am collaborating on with Greg Durrett, who you heard yesterday, Jesse Lee, and Matt Leese. So the idea is to make an Astro Copilot, essentially an astronomy assistant that helps astronomers deal with their data, search their data, explore their data, model the data, right? Now, why would you want to do that? Well, part of the problem is astronomy data is spread out across a broad range of different archives at different places on the web. This is sometimes hard to access. There's no text interface. You have to actually write a code query to access the archive and pull the data. And you need to, in order to understand it, have some pretty high level degree of background astronomy. So the idea is that we create this co-pilot, and then this becomes a mechanism by which we could have a conversation and do basic tasks using a text-driven interface. I don't know if you can read that very well, but so the user might ask what wavelengths of light can probe the structure and physics of a quasar accretion disk. And it would say optical, ultraviolet, and X-ray can probe the structure. Now, so in principle, it needs to understand astronomy relationships. You type this into ChatGPT, it doesn't give a bad answer, but it kind of gives a kitchen sink. It actually lists all of the wavelengths there are in the spectrum and why each of them are useful. But that's not what you want to do as an astronomer. You don't have to look through all of the different wavelengths. You want the specific ones that are the best ones. Then you might ask, okay, well, if those are the good wavelengths, what wide field surveys cover those wavelengths and to what depths? And you would say, okay, several wide field surveys cover optical, ultraviolet, and X-ray wavelengths. So it knows about the existing data, even if that's spread out across the internet. If you type this into ChatGPT, ChatGPT will give you some surveys, and it will give you, and they will be appropriately with a set of wavelengths, but it doesn't know anything about the limitations of those surveys. It doesn't know anything about the details or the actual depths, which is part of the question that I just asked. Do those surveys have published object measurement catalogs in the optical regime? Yes, Legacy Survey does. It has a photometric catalog with 2.4 billion objects. And it knows where to find the data, so connect it to where you can actually download the data. What other types of data would be useful to supplement the measurements? Spectroscopic catalogs from SDSS and DESI surveys can provide additional information, redshift distance. All right, so some degree of reasoning, not just what is there stored, but what physical properties you can extract from it. How do I construct a query to cross-match the catalogs from these surveys? And then it would give you an actual query that you could type in, and either you could copy and paste it yourself, or you could run it on, well, we also hope to create a science platform that will do this. I've played around with this with ChatGPT, and it sounds like it's knowledgeable. It will spit out some code, but often that code doesn't work and is not clear why. So maybe we need more training data, something specifically focused on astronomy data, not just being able to look reasonable code, but actually correct code. All right, then some much harder questions using the GRZ magnitudes. Can you determine the typical quasar colors and then make 5 images in these different bands of typical quasars? Each image should be 10 arc seconds on a side and also include the correct journal reference. So this is well beyond what ChatGPT can do, right? So it's not generating images. I don't know about the details of ChatGPT 4 because I don't have a subscription. But yeah, we can do this by and large and also connect it to the underlying database. So we want a tool that can also find, calculate, and plot for you. So this is like an AI astronomer, right? So I think in the next few years, this will be possible, one multimodal process at a time. I think we can build this up as a full tool because the ingredients, the research is there, but the domain-specific expertise has not been assembled to actually do this in a particular domain like astronomy yet. Do you have a question?
I'll wait.
You can ask a question now.
Like it was regarding like generating like using generative AI to like fill in the holes like for missing data. I was curious like in this particular field, right? Like how that will be like particularly like useful to you guys, because like you guys want like like actual like data, right? Like what's confirmed to be there or not, right? Not like a hypothesis or a theory that some AI just spat out.
Right. So I think there might be areas of low-hanging fruit. So for example, if you have instrumental effects or you have bad pixels, it might, if you have a good model that understands maybe what a galaxy looks like, it might actually be able to make a reasonable scientific prediction. And it could also do this if it had a model of the same galaxy but a different wavelength. I think that is doable. So it could then learn the underlying relationship between the different wavelengths and then fill in a pretty good prediction.
And
Yeah.
like, are these like models, have they performed better than like, your typical statistical models? I know you showed one method, but like.
Yeah. There's some statistical methods that try to do this, usually doing some kind of interpolation technique. I think we can do much better with generative AI, because interpolation is fundamentally not telling you about the richness of the underlying data. It's not, with these generative models, you could feed in additional ancillary information, like training on much larger data, which is relevant to that actual problem. Yes.
Thank you.
All right, so I hope I've convinced you that astronomy needs AI, but now I want to convince you why AI needs astronomy. All right, so I'm going to illustrate this, I'm going to use the HETDEX website. HETDEX is a survey, the dark energy survey, using the Hobby Eberly telescope at McDonald Observatory. So this is just the webpage. I just want to point out some things here. So first of all, astronomy data are public, plentiful, and non-proprietary. So you can see just right on this website, there's links to the available data. It describes the data. If you can't read it, it says we have millions of galaxies in our catalog. And I want to stress the non-proprietary part of things, right? All of our science is funded by NSF and NASA. That is the taxpayer dollars. So it will never be behind a wall. Astronomers are never going to sue you for using this data. I think OpenAI and Google are going to be buried under a huge number of lawsuits, given how they have treated our public data to date. This is not going to happen with astronomy data. Next is our community is a really friendly one. We have open codes and a collaborative environment. So yes, many of us do post on GitHub, so you could grab all that data. Maybe it's already in a variety of different trained models. But I think one of the differences, we really want this data to be shared and used. I'd argue that our data is also very interesting. That is, it's complex, noisy, and high dimensional. This is a galaxy spectrum. If you're an astronomer, that means something to you. Otherwise, you can see it's just very complex, but it's a very challenging data space. And if you want to work on noisy data or high dimensional data or just very interrelated data, this is an excellent space because we have all of that. And last, I want to stress that this is a safe test bed for experimentation. Right? So it goes out saying that no one is going to die from some AI astronomy trained model. I can give you this nice example. This this news clip was actually maybe from a year ago, from here, right here in Austin in West Campus.
Spotted in West Campus early Sunday morning. One driver was caught, then another, then another.
It was just insane. Like they need to get better at seeing where each other are positionally and lining up. I mean, all of them are like facing sideways in the street, trying to navigate around each other, even though they're all part of the same network.
Right. So this is just a downright embarrassing example. But there's obviously much more complex ethical issues with AI in society, something that Good Systems has been trying to address. But again, astronomy provides an excellent sandbox for this kind of thing. Yeah, you may do something embarrassing with your model, but ultimately it is not a harmful space to work in, right? So you can test out new ideas, try new things, experiment in this space, free from all of these other things that you have to fight through, whether you're using other public data, medical data, and other societal things, societal data sets that might have much broader implications on people. All right, so this brings me to my conclusions. I hope I convinced you that generative AI is a critical tool for solving astronomy problems. Astronomy needs AI, not just generative AI, all different types. Can bring a lot of value to our astronomy analysis. And I hope I have also convinced you that AI needs astronomy, that you too should check out astronomy data, download it, use it, train models with it, and come and talk to me, because there's a huge set of things that can be done, a huge frontier in which we can really improve the scientific domain of astronomy. All right, thanks.
Thanks so much. It was a great talk. So we have time for a few questions. Yeah.
You talked a lot about, denoising your data, and there must be, I'm guessing, many different types of noise that creep into the pipeline when you're coming up with those end images, right? And so one way to denoise would simply to be, not simply, but would be to take work on the images themselves. Another thing would be to, I assume, to get those images, you look at some data that was raw data that was obtained from a telescope. I don't know what that raw data looks like, right? But it doesn't look like an image. Another strategy would be, well, I'm going to look at that data, I don't know, shifted frequencies, whatever, and try and actually denoise that raw data because most of the signal is there. I mean, maybe there's noise from the instrumentation. Where's the right place to denoise, and how do you address all the different? Do you need to know what the noise looks like?
Yeah, that's a great question, and it depends what data you're talking about. So some of the data, like CCD data, does look like an image. It has noise, typical image-based noise. But there is instrumental noise, which is much more complex. It's not just white noise. And so part of the challenge is learning that underlying noise distribution. When we're training models to try and deal with this, what we do is we kind of do off-fielding. So you have some blank area of the sky, which doesn't have something interesting in it, but it does have a lot of noise, and use those noise characteristics to try to correct for whatever you're doing. And I think that is probably what is going to be needed. We factor that in terms of training generative AI models as well. That's only the third part of your question.
I was just assuming that there's like some raw data you get from the telescopes that doesn't look like an image.
Yes.
Is there any attempt at denoising that raw data?
Yes. So radio telescopes, we do something called radio interferometry, which is we have not just one telescope, but we might have 50 telescopes. And what you do is that creates sort of a sampled image of the sky, and you work with that in Fourier space. So there's this kind of Fourier cleaning process. But yes, that data is definitely more complex to work with. You don't work in the kind of real domain. But yeah, it's also hard.
Sorry. I have a good question. And so for the Astro Copilot, right? So those examples you gave are what an astronomy expert would probably, it's an astronomy expert level answer, right?
Yeah.
Do you have, or have you created, or are you hoping to create a set of golden question answers which you would then use to train? Like, is that the workflow that you're imagining for creating Astro Copilot?
Yes, that is part of it. And Jesse Lee is really an expert in this kind of this training, tuning, I guess you could say, the model. So yeah, at some point you would have to get professional astronomers, or more likely graduate students, to help us create a set of astronomy answers to use in the training. But yes, absolutely.
Sorry.
So I have two quick questions about the diffusion process. A, are you diffusing in latent space like image generation, or are you diffusing on the raw images? And the second one is, does the process always converge to the same answer? Because in diffusion, normally you have like noise at the beginning, and then the output depends on the noise that you started with. So does that matter or not?
I think it is diffusing in latent space. I don't remember there being a bunch of variation. That could just be how we trained the model. But yeah, I'd have to look at the details.
I have a question about the programming languages you use. I know a lot of astrophysics models are using older languages such as Fortran specifically. And when training with Python, I know there's a lot of issues and working between the two. I'm just curious how you kind of handle that, or if your models weren't in any of these older languages.
The simulations do use C and Fortran, they're just super fast. But the machine learning doesn't see that because it only sees the output images.
Okay,
So
so you just put it on top kind of.
yeah, it's totally decoupled. Mhm.
Thank you.
So when you're using the generative AI to predict star formation, obviously that is in relatively recent terms in the universe history. But I'm wondering if there's any adjacent work like this that's being used to investigate in the cosmic microwave background, like early universe.
Yeah, I would say in the astrophysics community, cosmologists are kind of on the forefront of a lot of the AI stuff. So I know they've used, for example, some earlier work used generative AI to generate galaxy lens images. Mathematically solving lensing problem is really hard, but you can do this using GANs, for example. So yeah, I think there's a broad range of work that is applied in cosmological context, but since that's not my area, I can't speak to more specifics.
Maybe this is the last question.
Just curious, so on the sort of the 3D modeling side, I'm assuming that like the first video you showed us of sort of 9 million year time scale timeline. Do you see generative AI being used in that front, stuff like Gaussian splats or these recent technologies for 3D stuff, or is it just like too complex and we're not there yet?
You mean using generative AI to predict the time evolution, to solve the underlying equations?
Yeah, something like that, or just any other sort of 3D application.
Yeah. So I think people are starting to use transformers for climate and weather prediction, and some of the models actually do quite well. And those with the right data sets are quite data rich, and they seem to be performing very well. But people have not used this in the astronomy context. The weather component is relevant. I've been following that because that's basically just gas dynamics, which is what I do essentially in the simulation. So, some of those areas of development might actually be very useful for astronomy. But one of the challenges is the very high dimensionality of the problem. One of the problems with, predicting, for example, from images directly is you're missing a lot of information. The simulations almost have too much information, extremely high dimensional, because you have all these physical variables for each zone in the simulation. And so getting a model that you can train sort of efficiently and is not super expensive to do that is a real challenge.
Yeah, so let's thank Professor.
Okay, thanks, so that we reached the end of our program unless Alex, you have more content that you wanted to.
No comment.
No, we're ending. So,